Hello and welcome to this video. So this episode is going to be very exciting because we get to implement a perceptron from scratch using Numpy. And before we get started, I want to mention some prerequisites that you need to have. So first of all, you need to understand the dot product. You need to know how to use Numpy. You need to understand the theory behind how the perceptron learning algorithm works. And optionally, I'll be using Matplotlib to plot some graphs for exploratory data analysis. And even though that is not required, I would suggest to you that you look for the Matplotlib data visualization playlist on my YouTube channel and then watch the videos there because they will give you enough understanding. It is not required to know how to use Matplotlib for this video, but because the visualization helps with the understanding, I will suggest that you go to my YouTube channel and look for the Matplotlib data visualization playlist and watch the videos there. Okay, so let's get started. So this is a continuation of where we left off from the previous episode where I gave you the theoretical explanations into how the perceptron learning rule works, and today we are going to implement it. And so this is more like a hello world in your deep learning journey. So let's get started. I'm going to start with some import, and you'll see some new things, but I will explain anyway. So from sklearn dot dataset import load iris. So basically we are going to use a data set that is made up of different species of flowers, and we are going to train the perceptron to be able to distinguish between the different species of flowers. And the library that makes this data available to us is scikit-learn, and so I'm importing the dataset module from scikit-learn. And so from sklearn.dataset import load iris. The load iris is a function that will return a data bundle that contains the training features and then the labels. And so basically it is going to give us NumPy arrays that we can manipulate and also use to train our perceptron. And as usual, we are going to import NumPy as NP because otherwise we can't do this easily. And I'm going to import matplotlib.pyplot as PLT. And I suggest that you look at my data visualization playlist on my YouTube channel. So I have all these imports. Let's run it and make sure everything is okay. And this is taking quite some time, but I hope it will finish very soon. Okay, yeah, so we have all our import. Let's go ahead and then load the iris dataset. So I'll say iris is equal to load iris, and I'm going to print the feature name. So I'll say print iris dot feature names. I'm going to explain to you what you see. Okay, so like I explained to you, the load iris function in scikit-learn gives us some data sets that we are going to use to train our perceptron. And what is involved in this data set are the sepal length of the flowers, the sepal width, the petal length, and the petal width. So basically, these are measurements of the sepal length, sepal width, petal width of 3 different species of flowers with the corresponding labels. And we are going to train our perceptron algorithm to be able to distinguish between 2 of these different flowers. And so when I print the feature names, it's basically telling you the column headers for each of the features in the training data set. And I'm going to print the target labels as well. So I'll say print iris.target names. So what we see here is setosa, versicolor, and virginica. So what this basically means is that the flowers are grouped into 3 categories: setosa, versicolor, and then virginica. And we are going to just select 2 out of these 3 flowers that we want our perceptron algorithm to be able to distinguish between. Don't forget, from the previous video I explained to you that the perceptron algorithm only works for linearly separable data. and the output labels should be 2. So we can't use it with these 3 classes of flowers. That is why we are going to just select 2 of them, and then we train the perceptron to be able to classify any unseen data point into either one of them. Okay, so now we have been able to inspect the feature names and then the target names, but what about the data itself? To get the data, I'm going to store the training data in a variable called s, and I'll say iris.data. I'm just going to do this, and I'm also going to store their corresponding labels into iris.target. So this is how the scikit-learn module organizes the data set for us. It gives you data, which is actually the features, and then target, which is actually the label. So if you take an index in the features, in our case the x, if you take an index in x and you take an index in y, what you're basically doing is you are matching the features to their corresponding output. Okay. All right, so let's inspect their shapes. So I'm going to inspect their shapes here, and so I'll do print s.shape and then y.shape. Let's see what we get. So basically we are seeing 150 by 4 and then 150. What this means is that we have 150 rows, each with 4 columns, and each column corresponds to the feature names here. So the first column is the sepal length, which is measured in centimeters. The second is the sepal width. The third is the petal length. The fourth is the petal width. Okay, so let's just print a portion of the data and see. So I'm going to just print let's say first 5 of them, and let's see what we have in here. So basically this is one row of measurement for a particular flower. This is another row of measurement for a particular flower, and this is also another row of measurement for a particular flower. Let's print for the first 5 rows of the labels as well, and let's see what's in there. So you can see that what this basically means is that this row has the label 0, and the label 0 is a setosa. Now the scikit-learn module comes with the labels arranged in order, so you can see that the first 5 are all setosas, but I'll show you how we can shuffle so that we can have versicolor and virginica and all those guys coming in there. I am sure by the time we go to, let's say, if I select from 100 to, let's say, 105, and then I do the same for this, you can see that we will be in a different type of flower. So this is 2, which stands for virginica. Okay, so I'm going to delete these cells because I just wanted to use them as examples for you to see what's going on. All right, so there is one Numpy function, np.unique. If you pass a one-dimensional array to np.unique, what is going to give you is the unique items in there. Remember that the y is the target, and it contains a lot of zeros, a lot of ones, and a lot of twos. But once you say unique, it's going to bring you the unique items that are in there. So it's basically telling us that in the y numpy array, we have the value 0, 1, and then 2. Okay, these are all not needed in your implementation for a perceptron, but I'm just trying to build your understanding from here onwards. Okay, so we have seen that our X array contains the information, that is the measurement about the individual flowers, and then the Y array contains the labels that have been assigned to the individual items, the flowers that have been measured already. And there are 3 different targets, so 0, 1, and 2, and you always know that the perceptron algorithm only works for binary classification where the data set is linearly separable, and so we cannot use all 3 flowers to train our perceptron. So we are going to just choose 2 of them, and for that I want us to be able to distinguish between just setosa and versicolor. So this is why you need to understand NumPy, because everything I'm doing here has been explained in one of the videos in my NumPy episode, so you would want to learn that, otherwise you get lost in this video. So I'm going to create a Boolean mask. that is going to select the zeros or the ones. So I'll say where y equals 0 or y equals 1. So this Boolean mask is going to give me all the flowers, the measurements, which are setosa or versicolor, and I'm going to get their indexes, and I'll use it to select the corresponding features from the X array, and I will select the corresponding labels from the Y array. All right, so I'll come down here and use the Boolean mask to select from the feature data array. So I'll say mask, and I'm not going to use all 4 columns for the training, and I'm doing this not because the Perceptron cannot handle 4 columns. It can, but for simple visualization, I'm going to just use 2 columns, and the columns that I'm going to use are the sepal length and the petal length. So I just want to use these 2 columns to train a Perceptron, so that when I give the trained Perceptron an array consisting of sepal length and a petal length, the perceptron should be able to tell us which flower it is likely to be. So I am using the index to select in the X array where their target labels are either 0 or 1. And I'm also going to select just these indexes for the column 0 and then 2. So basically I'm saying I want the entire rows, and then I want just the index 0 and index column 0 and column 2. Once again, make sure you understand Numpy, otherwise you are going to get lost here. So I'm going to select the mask. So basically I'm just selecting the targets which are 0 or 1. Now let's see something. Let's see what happens here. If I print np.unique y, you can see that now we have only the target 0 or 1, and so this is setosa and versicolor, and the same applies for the X array because we use the Boolean mask to select those flowers that are either 0 or 1. Great. So let's go ahead and inspect the shapes one more time and see. So I'm going to print x.shape, and I'm going to print y.shape. Okay, so we can see that there are 100 flowers, and each of them has 2 columns. And the columns, like I told you, I am using the sepal length and the petal length. Not because we can't train a perceptron with all 4 columns. We can, but because this is our first video, I want to just use 2 columns so that we can visualize things for better understanding. Okay? All right. So now I am going to group our X data into the setoses and the versicolors, because we want to plot to see that they are naturally grouped or clustered together, and so it makes it linearly separable. So I'm going to say my setoses are X mp.where y equals 0. So this is basically selecting from the features array where the corresponding target is 0, because if you look up here, you can see that 0 is setosa and 1 is versicolor. I'm going to do the same for my versicolor. So versicolor, I'm going to call it versicolors. It's equal to x mp.where y is equal to 1. So I'm basically selecting from the features where the target is equal to 1. Okay, so now I have grouped my setoses and my versicolors. What I'm going to do next is to plot the setoses and the versicolors on a graph so that we can inspect visually to know if the data set is linearly separable before we even make an investment into building a perceptron to learn how to classify new data points for us. And this is where you need to understand Matplotlib. But if you don't understand it, I will suggest to you that you write the code as I am doing, and once you're done, you can go to my Matplotlib playlist and then watch the videos there. You understand why the code is the way it is. So plt.scatter. So I'm going to plot the setoses, and I'm going to plot the first column on the x-axis, and I'm going to plot the first column on the x-axis, and I'll plot the y the second column on the y-axis. So sitoses, I want the entire array, I want the first column, and I want to color them red. And I'm going to assign a label of sitosa. Okay, and I'm going to do the same for the versicolor. So I'm going to plot the versicolor here, versicolors. So I'm going to replace this here, replace this here. I'm going to make it blue, and this is going to be versicolor. Okay, now I'm going to set X label and Y label on my plot. So plt.x label. So on the x-axis, I have plotted the sepal length, and then on the plt.y label, on the y, I have plotted, so this is sepal length and then petal length. Okay, so I have plotted a petal length, and then I will show a legend. So legend, and let's show this plot to see what's happening. So what this code is giving us is this plot that you can see right here. And what I basically did in the code above is to plot all my sitoses in red and then plot all my versicolors in blue. And I plotted the petal length. It's just a scatter plot of the sepal length versus the petal length. Okay, and you can see just by visual inspection that this data is linearly separable, because if I start from this point 2, I can draw a line all the way here to clearly distinguish between sitoses and versicolors. So this means that it's possible for us to create a perceptron to be able to learn how to distinguish between versicolors and sitoses based on just the sepal length and the petal length. Okay, so in the next cell, let's begin to build our perceptron algorithm, but I want us to inspect our x and y data for the last time so that it's fresh in our mind. So I'm going to say x.shape and then y.shape. So let's see. Yes, so our features is made up of 100 rows and then 2 columns, and the first column is the sepal length, and then the second is the petal length, and the labels are also 100 because we have 100 rows here. So each feature or each training example should have a corresponding label, and that is what is in the y numpy array. Okay, great. So let's go ahead and build our perceptron. First of all, I will import the sys module from Python because I will need to use it to flash my output stream when I'm printing something. But the core is in this class we are going to create. So let's create a class called Perceptron. And it's going to inherit from objects. This is basic object-oriented programming in Python. So if you don't understand, you want to check your Python knowledge. Okay, so first of all, we will want to tell it how many features will go into the perceptron, and I'm going to call that input dim, the input dimension. In our case, we know that our input dimension is 2. The input dimension is basically the number of columns in our training data set, okay? But we want to make our class generic so that you can pass in different data sets and then the perceptron should be able to learn with it. Okay, so from the previous video, I told you that the perceptron uses weights and bias to be able to assign importance to each of the features that comes with the training data. And we can initialize it randomly or we can initialize it to zeros. In our case, we're going to initialize it randomly. So I'll say solve.weight. So we're going to create our weight matrix, and it's going to be mp.random.normal. We are just creating some random numbers that are normally distributed with a mean of 0 and a standard deviation of 1. And once again, this is one of the first things that I talked about in my NumPy series. So if you don't understand, you want to check that. Okay, so we have initialized our weight vectors vector randomly, and we are going to initialize our bias as well. So our bias is going to be mp.random.normal and then you're going to say look is equal to 0.0, standard deviation is equal to 1.0, and I just want 1. Okay, so the bias is just one number, and the weight, the weights dimension should match the input dimension, because each input feature should have a weight assigned to it. So that is what we have done here. That is it for now, and then we are going to create our threshold function. In the previous video, I told you that the first thing that the perceptron does is to calculate a dot product or a linear transformation of the weight and the input features, and once it is done, it passes it through a threshold function or an activation function. So we are going to create that threshold function or activation function. So I will say dev activation, and then the activation is going to take a prediction from our perceptron, and what it's going to do is it is going to return 1 if the prediction is greater or equal to 0. If it's greater or equal to 0, otherwise 0. I explained all this in the previous video, so if you don't understand anything in this video, I suggest that you go back to watch the theory on perceptrons before you try to implement it, otherwise you'll be confused. Okay, so now we have our activation function defined, but you remember that even before we come to the threshold function, we need to have already performed the linear transformation, which is the dot product on the input features and the weight vector before we pass it to the activation function. So we are going to create a function called predict. So def predict, and is going to take in data. The data is going to be whatever examples, training examples, or never seen before data that we want the perceptron to make a prediction on. Okay, so this is going to be, it is going to apply the activation, to the dot product between our data and then our weight. So our weight, how did I spell that? GHTS. And I'm going to transpose it. The reason why I'm going to transpose it is, if you see here, our data is 100 by 2, okay? And then we have created a weight that is a vector that has 2 elements. And you remember that there is a condition for matrix multiplication to work. So if we transpose our weight, then it makes it possible for us to do a dot product between our input training data and then the weight matrix. All right, so now that we have created our prediction function, the next thing for us to do is to define a function that actually trains the perceptron. Okay, so I'm going to say def train, and then it is going to take our input data and then the target and then the epochs, because I showed you in the previous video that you have to repeatedly do the update to the weight up until the point where there is convergence. So the epoch is the number of times you want to go through the entire training data set, and we also spoke of the learning rate. I'm going to set it to 0.01 by default, but you can also change it if you want to. Okay, so first of all, we start by keeping track of how much errors we make as training progresses. And the way we know that the perceptron is learning is that the number of errors we make, the perceptron makes, should reduce as the training proceeds, as it goes on. Okay, so as the number of epochs increases, the errors that the perceptron is making should be reducing over time. So I'm going to create a list that will store the losses that we are making. Then I'll say for epoch in range, so I'm going to do epoch number of times. Okay, so epochs plus 1, and then what I'm going to do is, for each epoch, I want to keep track of how much error or how many errors or how many misclassifications the perceptron is making. Mind you, it will start off randomly, so it will make the biggest errors on the first epoch, and then it will learn. So the second and all subsequent epoch, it should be making less errors. Okay, so I'll call this the epoch loss, and that is going to be 0. And then what's going to happen is we want to loop through each training example and label pair, and then call the perceptron to make a prediction, and then see how wrong we are, and then we will update the weight to correct the mistake that the perceptron is making over and over and over. Okay, so I will say for data target in zip, and if you don't understand the zip function in Python, you would also want to check my Python Nugget playlist. I have explained what the zip function does. So basically what we are doing is, if you call train, you are going to pass in your X and Y. The input data is going to be our X, which is the training features, and then the target is going to be our target labels. Okay, and so the zip is going to do a pairwise grouping of each training example and the corresponding target. And then once we have it, what we're going to do is, first of all, we will let the perceptron make a prediction. So we say prediction is equal to self.predict. So it has to make a prediction on the training example that it has seen. This is the point where I explained in the theory video that if the expected target is 1 and the perceptron predicts 1, then it does no update to the weight based on the mathematics I showed you over there. So that is basically what we are turning into code in here. So we have our prediction, and then we want to see how off we are. So we say error is equal to our target. The target is, in the training example, is this class supposed to be 0 or 1? So if we subtract the prediction from our target, then we know whether we are wrong or we got it correct, whether the perceptron got it correct or it got it wrong. So if target is 1 and prediction is 1, then the error is 0. Otherwise, you calculate the error, and then the error will go into how much changes we make to the weight vector. Okay, so we have our error, which is equal to our target minus our prediction. Let's create a value called update, which is going to be how much we want to change our weight vector, and that is going to be equal to the learning rate times our error. Okay, that is going to be the learning rate times our error. And the next thing we want to do is, because there is an error here, it could be 0, it could be a negative number, or it could be a positive number. The most important thing here in the learning rule is how off we are. We don't care whether we are off in the negative direction or off in the positive direction. It's like when you are throwing, when you are playing the game of dart, your target is to hit the center. If you don't hit and you miss, you don't care whether you missed above the center or below the center of it. You just want to know how much you missed, and then that is what goes into the correction. And so to not care about the sign of the error, we are going to square the error, and then we will just add it to our epoch loss. So I will say epoch loss plus is equal to error to the power 2. That is how we are keeping track of how much errors we are making for each epoch in our training. Okay, so at this point we come to update our weight. So we say self.weight is equal to self.weight plus the update times the data. If you don't understand this formula, I strongly suggest that you should watch the theory video, the video that explains how the perceptron algorithm works. Otherwise, you will not appreciate this video. The videos I have made in this series are meant to be watched in order, so don't skip any one of them because you're excited about learning how to implement it. The understanding is more important so that you can also implement this without actually looking at my code. Okay, and then in the perceptron learning rule, you realize that the way we update our bias is similar to the way we update the weight, but then we don't multiply it by data, so we just have to update. Okay, and then once we are done for that particular epoch, we are going to append the epoch loss to our losses. So we say losses dot append epoch loss. Okay, now after each epoch we want to print out how much errors the perceptron is making. So I'm going to do print f, and if you don't understand this construct I'm using here, you can also watch my Python nuggets video, because I have a video on how to create the illusion of animation with test in place using the carriage return, the print function, and then the sys module. That's what I'm using here. Basically I'm just printing out the epoch over the number of epochs that we really want to do, we want to train, and then I'm also printing the loss for that particular epoch, and that is going to be my epoch loss. Yes, and I will say end is equal to this, and then I will say sys.std out.flash. Okay, so at this point we are going to return all the losses, because after training we want to be able to plot the losses over time to know whether our algorithm was learning well or it wasn't learning well. So at this point we have our class that represents our perceptron with very simple Numpy codes, and if you don't understand, once again I suggest that you watch the video where I stood by the board and I explained to you how the perceptron learning algorithm works. Okay, so at this point let's create a perceptron and let's train it on our flower data set, and let's see how learning improves over time. So I'm going to create a perceptron. So perceptron, and then the input dimension. So input dimension is equal to 2. The reason why it is 2 is, like I showed you here, our training features is made up of 2 columns. I think the sepal length and the petal length. So we have just 2 input features that comes in there. Okay, so now let's say our losses is equal to perceptron.train, and we are going to train it on our x and y, and then we are going to do it for, let's say, 50 epochs. Okay, now let's run this. This is the moment of truth, and woo, unbound local variable target referenced before assignment. So it means there is a mistake somewhere here. Data, let me look through this code and I'll get back to it. So I have seen where the error was. So basically I used target instead of target. So the target is supposed to be the y values, your expected predictions, and that is what I want to call the zip function over. But I said for data target in zip, input data target instead of targets, this is what I want to zip. So I just change this, and then we should be able to train our perceptron. So you can see that our perceptron has trained for 50 epochs and it is making a loss of 0, which means our perceptron has learned how to map each of the training examples to their correct output label. How do we know if the perceptron learned correctly or not? First of all, let's try to inspect what the weight and the bias are now. So I'm going to print p.weight, so p.weight, and let's see p.bias. Let's see what values are in there. So it's telling you that this is the first weight, the second, and then this is also the bias. So we started off with a random number, and the perceptron algorithm through training has found out the correct weight and the bias that it can be able to use to distinguish between the different types of flower species. And so let's go ahead to plot our loss over time, because that is how you get to know if your perceptron algorithm has been implemented correctly or not. So I will say plt.plot, and I'm going to plot my losses. Let's give it a label of loss, and then I'll say plt.legend. So Let's see. All right, so what this means is that our perceptron algorithm started off by making 12 mistakes. So on the first epoch, when it started with a random weight and bias, it made 12 mistakes, and then it's reduced it over time. By the time we reached about, I think, the 11th epoch, the perceptron had learned how to classify all the input data correctly. And so this is how you get to know if you have implemented your algorithm well or not. Okay, now this video has been long. I will cut it short, and then in the next video we look at how to plot our decision boundaries and stuff like that. But before